All right, so we have finished the properties quiz, and for the Algebra 1 students, that is still ahead for them. If you remember how much work you had to do last year for that was pretty important. So what we're going to look at today is continuation of the domain and range of functions, and we're going to finish up the chapter 2 today. And so by the end of this week, we'll have chapter 2 finished, and we'll be able to move into the next chapter next week. And so if you'll notice, it says to watch videos 3.1 to 3.4 before class next week, so that you have an idea where we're going. All right, now we already have in section 2.3. This was the handout I gave you last week that has those graphs in it. All right, and for this week, you're going to do the even number problems 14 through 24. It's just more of the same. All right, and you're supposed to be trying to be able to figure out what is happening with whatever the input is, and what based on the input, what is the output looking like? Is it going up? Is it going down? Is it constant change? Is it varying change? And all those things are part of that analysis. And in Algebra 2, then we're going to be putting a lot of those things into equations and graphs. All right, and you're going to need your graphing calculator today, so if you don't have it out, get it out. All right, so now what I want to do is begin to look at some of this. All right, I'll go back over the things. Okay, so first of all, domain. By definition, domain are the values of x for that particular problem. There are some problems where I would give you something like this. Okay, and if I were to ask you, what is the domain for this set of points? What would I be asking you to give me? If I said, what's the domain?
The value of x.
The values of x. So, the domain, right, using our notation terminology, the domain is the set. Oh, wait a minute, I'm sorry. The domain is the values of x such that they are part of the set, and in this case, I would say 3, 7, -3. The domain are the values of x such that they are part of the set 3, 7, -3. All right, now what would you do for range?
You do the values of y.
The range would be the values of y such that they are part of the set 5 to, I would say 9, 11. Should put them in numerical order probably. Right. So that's looking for the values that are the range and domain. And what we had on the homework is that we had a set that was given, and then that is going to change what the graph looks like. And we'll get into that a little bit more at the end. Okay? So, the domain is the set of all x's such that x is greater, and this is in a dual inequality. Right? It would be showing you a line segment of some sort, and then here's the range. Now, where this is going to come into play for your testing, what's wrong here? What is this? Now, let me go to this one because it's easier. Okay, so we have this right here. See, I want that over on that wall so I can write on this. I'm gonna, let's see. Let me see if I can just turn this. Yeah, this may work.
Oops.
What happened?
Yeah.
You push the thing.
Oh, I can push the wrong button. Like this one.
Yeah.
All right, so let's say that I have something that's here. It goes like this. Here. Now, what is the domain of this function?
Negative.
All right. Okay. In this case, the domain, the last part is here, but it's open, right? And this one is here, and it's open. Right? And so domain such that x is greater than -5 and less than 3. Now, what about the range?
It's 6 and -2.
All right, the range is the set of y's such that, and again, we're down here at -2 is y is +6. All right, and we have identified that squiggly range and domain for that graph. All right, so that's a test problem. How hard is that? Not hard. Okay, what would have happened if I would have had this thing in here?
Equal
Then
to.
these would have been equal. No problem. Just a thing. Okay, now that's the first question. The second question has to do with function. Okay, a function is a relation between x and y such that every domain point has one and only one range point. So every domain number has a unique range. All right? Therefore, x does not repeat. Because if it does repeat, then you have an x going to two different y's, and that's not a function. Okay? All right, so first of all, right, if I look at this point here, and this point here, it looks like that I have 0, 1/2, and here I have 0, 4 1/3. Okay, so do you notice that I have an x of 0 twice? So my range is not unique because I can go to either one of those things and be on the graph. So therefore, this is not a function. Okay? Now, if I had something like this, here I have my range, the highest is 3, and the lowest is almost -3. So let me put it down here just so it's exactly -3. All right, but in this case, if I use what's called the vertical line, over here I went through actually 3 points, because I also had this one down here, which was 0, -2. So this fails the vertical line test to prove it's not a function. This one, all my vertical lines will only pass through this graph in one location. So this is a function. Okay? So, 2 ways. Number one, you look at the points. If there are no repeats on the x, it's a function. If you get one of the points where you have the same x and different y's, you do not have a function. function. Right now, all that is a definition. One of the nice things about algebra is that when we work with functions, if you're trying to solve for x, there's only one right answer, because in a function, every x has a unique y. All right, that's one of the reasons that mathematics is the way it is because that gives us a little bit of stability when we begin to talk about those things. Okay, so a function passes the vertical line test. It only goes, a vertical line will only go through it once. That means for whatever vertical line, wherever it hits the x value, that x value has only one y number, so you're identifying it as a function. Alright, so if I give you something that looks like this, a function that looks like this, is that a function or is it just a relation?
That'd be a relation.
Why?
Because it doesn't go through two of the same numbers on the vertical.
Well, let's look. How many times does these vertical lines, how many times do they cross that graph?
Oh, so it would be a function because it only goes through
It would be a function because it passes a vertical line test. Right? However, if I give you something like this, that's a function because it passes the vertical line test. But if it went like this, that would not be a function because it fails the vertical line test. And in this case, I would have 2, 1. I would have 2, -1. And I would have 2, it looks like negative 2.7. Whatever those numbers would be. And these points mean that the x value is not unique. There's not just one x. There's two y's for the same x, so this is not a function. And the last thing I want to do in a map, if this is the domain and this is the range, if I have, say I have 4 here, going to 9. And I have 7 going to -3. And I have 2 going to 15. Okay. The points 4, 9, 7, -3, 2, 15. All right. If you look at this, there are 3 numbers in the domain. Each number in the domain has 1 arrow leaving it going to the range. So that means that this is a unique relationship. What would happen if I had this? Now, how many different points do I have in the relation? I have 4, 9, 7, 9, 7, -3, and 2, 15. But because the 7's repeated in the domain, it's not unique, so it's a relation, but it's not a function.
Does it go through the y-axis?
Because it goes to 2 different y's. So therefore, if you were looking at the points, you would have a repeat in the domain. When you look at it this way, because this 7 can go to 2 different y's, that's not a function. If the function has to have 1 line leaving it if it's in a map. If it's in a list of points, the domain cannot repeat. And if it's a graph, it has to pass the vertical line test. Those are the 3 ways that you begin to look at functions. Okay, first one 1 line leaving on the map. Second thing, in a list of points, no repeats of the x. And the third thing, the graph passes the vertical line test. Okay? Right now, that takes care of the function part, so now let me, whoa. Now that was because I didn't move anything. All right, so let's say that I give you this one. Yes, it's a function, just thumb up. Yes, it's a function. No, it's not a function. All right, you have to vote. Yes, it's a function. No, it's not a function. All right, everybody did yes. Why?
Because of the x-axis.
Because all the x's are different. Now, if we were doing an inverse, we would switch the x's and y's.
Then it would be y.
And then the inverse is not a function, but that is a function. Okay. But what happens if I did this? Now it's not a function because -2 on the x goes to two different locations. But wait a minute, they're both the same, so that doesn't even work. Never mind. But you got the idea. All right, so those are the things that we're looking at. Now, let me get back to where we were. Okay. All right, so we've gotten this part. So now we look at page 65. And I'm going to see if I can move this back because I think I'm done with the basic writing that I need on that. So let me put this back here. All right. So a relation is a set of ordered pairs. For the relation to be a function, the domain has only one arranged value. So the x's do not repeat, and it also passes the vertical line test. Now, t-chart. The t-chart comes from this. This is x, and this is f of x, or y. That should be familiar. Now, if f of x is equal to 2x plus 7, then if I give the domain as 1, 2, 3, -1, -2, then I can create a t-chart that has the y values or the function's value given that domain. And of course, how would you do that?
Insert the
You
number.
would replace this, and this particular one you can probably do in your head. So we have 2 plus 7 is 9. 2 times 2, 4 plus 7 is 11. Right? And then we have, now watch. All right, what's this? This is the slope of 2, right? 9, 11, and 13, because they're all in order. All right, if it's -1, this will be 5. And then that'll make this 3, because I'll have -4 plus 7 is 3. All right, and so this is still the slope of the line, and the slope is 2 over 1, right? Every time the x changes 1, the y changes 2. Right, that takes our slope from Algebra 1 and puts it just a little bit deeper understanding. Okay, does it make sense? Question about that? Okay, good. All right, so when you have a relation that is a function, you can do a t-chart, and then you can plot the t-chart. But we have a calculator that's graphing. Okay, so let's put in y equals, turn your calculator on and go to y equals, and put 2x minus 5. All right, now 2x minus 5, when you graph it, what happened here?
What did you get?
All right, when you graph 2x minus 5 in the y equals, and then you go over to graph, you should see a straight line. Now, the size of the window makes a difference. Okay, so let's press window. See where window is up at the top? Second one from the left on the very top. Press window and do x minimum -10, +20 for the y max. The change of 1 stays the same. And then y minimum -10, y max 20. And change y is 1. And don't worry about the rest. Now when you press enter, you should see something like that
Oh, wow.
when you go to the graph. And now the reason I'm showing you that is because depending on the equation, the window may have to be adjusted because the values of y or the values of x are outside your window. So you've got this small little window, but it doesn't actually show everything. That's the reason that we're changing it. Not, okay, go y equals. All right, and then here, then press, or you got it. Because your window is that negative. Yeah, you did it. These other ones don't worry about it. Okay? All right, now. So we were on page 65. Okay, 65 is relation versus function. Okay, what makes the difference? A relation is just is an ordered pair, an x related to a y. All right, for instance, here's a relation: Georgia, Atlanta, New York, Albany, New Jersey, Trenton, Pennsylvania, Harrisburg. What's the relationship?
The state and the city.
State versus capital city. State versus capital city. And so if I gave you California, you should give me what starting with S? Sacramento. There you go. Okay, that's a little bit of social studies. But the point is, that's a relationship. Now, here's the question. Does it also represent a function?
Yes.
Why? Because what did we start with? We started with a state, right? Are states unique as far as their names are concerned?
Yes.
Okay? And does every state have only one capital now?
Yes.
So therefore, it would, but what about Georgia? If you did if you did Georgia history, Georgia's had, I think, 4 different cities as capitals.
Yes.
All right? And so it depends on the time period, right? And so is capital city in the state of Georgia, is it a function?
Currently, yes.
It could be no, but it also could be yes, unless there were 2 capitals at the same time. See, if there were 2 capitals at the same time, and I said, I'll meet you at the capital steps, you could be in one city, I could be in another, because the capitals were not functions of the state. But if there's only one, then it would be a function, and we'd be able to communicate that way. Okay, so that's the function part. When you are looking at these graphs, time is normally independent because time moves regardless of what you're doing. Time is moving, right? So most of the time you'll find that the time measurement will be on the x-axis because it's independent. All right, and same thing with number. The number of something will be on the x-axis, and what you do with the number will produce the value of the y-axis. And so a lot of times counting how many, like how many hours, that's usually independent because it's time. right? How many, one of the things is how many cans you get. If you got 8 cents a can, then the graph looks like what? It's a line, and the value along the x-axis is number of cans. You multiply it by 8 cents, that gives you the cost. So a lot of times cost will be a dependent variable on the y-axis, and counting or time is usually on the x-axis. Okay, that will help as you try to be able to get those graphs there. Okay, now, next one. I think we know this. What is an asymptote? If you don't have this down, this is important, because we are going to see asymptotes. All right, asymptote is a line that's approached but not crossed, and usually it's shown as a dotted line. Okay, so age and height. Okay, why is there an asymptote up there?
Because your height gradually stops while your age
Because, right, it reaches a limit based on genetics, right? But also, in general, that line has got, let's say that line is 13 feet, right? Some tall people may approach what? 7 foot, maybe 7.5 feet tall, some people, but they're not going to be in the 10, 11 foot range, right? And so there's an asymptote that's an upper limit. Now we would like to get that asymptote to be as close to the actual limiting factor as possible, which is the calculus, right? Which we're not ready for. But the asymptote is a limit there. Okay, now, if I give you the equation 1 over x, there's an asymptote. Okay? Now, who wants to make a guess at where the asymptote could be? All right, let me ask you this way. Is there a value of x that you will never be at if your function is 1 over x? All right, think of it this way. Is there any value that x may not be? Can't be 0, can it? So, therefore, if I was graphing this at x equals 0, I have a vertical asymptote. I'll never cross that line. I can approach it from the left, I can approach it from the right, I'll never be on it, and so therefore I can never cross it. That would be called a vertical asymptote. Right? So there are horizontal asymptotes. Right? For instance, if you had absolute value, the absolute value of x can never be what? All right, wait, let me change it. The absolute value of x plus 1 can never be, this can never be 0, so this graph has a horizontal asymptote at 1. Because the lowest value that this has is 0. 0 plus 1 is 1. So I have an asymptote right there. I'll never cross that line. All right, that's the type of thing that we understand on asymptotes. Don't worry about the rest of that. That's deeper in Algebra 2. But the term asymptote is a line that you approach but don't cross. And there can be a vertical or there can be a horizontal. Okay. Okay, now if you look at C, the square root of that number. Okay, now here's what I want you to do. We're going to start to use our calculator. Let's go into y equals And let's put y equals c, the one that says c, the square root of negative x plus 2. So go to y equals, clear what you've got, and go second x squared, square root of negative x plus 2. And then look at the graph. What does your graph do?
It got lower than the
All right, and so it starts coming down, but then why did it stop? It stops because I have a limit right here. When this value is when this value is 3, what is negative 3 plus 2? Negative 1. Can you take the square root of negative 1? Is it real or is it imaginary? Can you multiply a number times itself and end up with negative? No. And so, therefore, I have a limit in my domain. My domain has to be limited to only values that are 2 or less. Because it's minus. Right? So if this is negative 3, then the opposite of negative 3 is positive 3, that'll be 5. But if this is 1, I'll have 2 plus negative 1, which is still real. But if this number is 3, or actually if it's 2, I'll have 2 plus negative 2, which is 0, and that's the last point on the graph. Okay? So, again, those are things that you're going to learn, is that there's limits on the domain because we need to be in the real number system. Or, the other way that you can limit it is if, like you had on the homework, if I give you a number set, that could also limit the domain. Now, okay, we're going to look at table. When you press graph, you got what the graph looks like. When you press second table, if you'll notice, you should have an error. Okay, that's because those values will be a square root of a negative number, and so it doesn't work. Now, the other thing I want you to look at, what's the change in your x numbers? Notice it's changing by 1. All right, when back in the window we had minimum, x maximum, and then it was SCLx, the change of x. If you wanted to change this by a value that was less than 1, then you go to that third one and you change it. Okay, so, all right, and we'll get into that later because that's needed in college algebra. But right now we have a limit of a change of negative 1. Okay. All right, clear? Questions on that? All right, so that's the graph. Now let's look at, when you look at D, it says the absolute value. All right, and this is actually a trick problem. To have the absolute value, you actually have two conditions. If the y is positive, then what will you have as your graph? It will be negative x plus 2. All right, okay, so let's do this. Go back to y equals, clear what you've got, and let's put negative x plus 2. Now look at that graph. All right, negative slope, right? Linear graph. All right, now, if we put in also, go to y, back to y equals, drop down to the second one, and put x minus 2, because if the value inside the parentheses was negative, we'd have to take the opposite of it, right? So I'm going to put x minus 2. And then don't erase them, leave them both up. And what you're going to get, the y has to be positive. So look at your graph. Your graph is going to come from the negative side. It's going to be going down until it reaches 2. And then it's going to jump to the other graph and go up to positive infinity. So it's going to start at positive infinity when x is negative. It's going to come all the way down till it hits the line where x is 2, and then it's going to jump to the other graph because the y was absolute value, therefore the y has to be positive. That's the whole point. Okay? So when you have graphs, it's possible to take two graphs and be able to represent one particular situation, especially if you have a situation like y squared. What happens to an x value if it's squared? It becomes positive, right? So the y value, if it's y squared, then we're going to take the square root of it, but we have to only have the positive because we can't take a negative square root. And so what happens is half the graph disappears. All right, and I'll show you that in a second. Okay, if you have that's y equals x squared. Is that a function? Why? Because it passes the vertical line test, and we know also from the fact we've been using it, it's a function. Okay, if I change this around and say y squared equals x, what I've done is this. Is that a function?
No.
Fails the vertical line test, right? And so what I have to do, there it is. So I have to take half of it off. You know what that is? That's a square root function. Because if I take this, if I take the square root of this, the square root of this, we get y is the square root of x. But not for all x, only for the places where that's positive. Okay. Yeah. Again, that's just an introduction of where functions can go. Right? And in college algebra, what you have to do to be able to represent it, I'll show you. I'll show you. All right, go to y equals. This is cool. All right, go to y equals. Clear both of them. Okay. Now go back to y1. And put square root x. So you go second, square root x. Then drop down to y2 and put the opposite of square root x. And then look at the graph.
Like negative square root x?
Huh? So you can get both of them, but they're separate because the graphing calculator is looking for a function. Okay. You should have in y equals square root of x, which is second x squared, brings your square root up, and then just type the x number. All right, and then in the second one, in y2, you put y2 equals negative. It has to be the one under the 3, the negative square root of x. And what it does, it takes the parabola function, if you look at this, it takes the parabola function, which is normally a U shape, and it turns it sideways, but it's made from two different graphs because both of them are functions individually, but together they don't pass the vertical line test, so therefore the graph won't let you do it, the calculator won't let you do it as one function. That make sense? I'm not trying to confuse you, but it's important that you recognize that. So what I like about the new calculators, I don't know if you can see that, I got two colors. The older calculators are all gray, right? And so it's not as simple to be able to see, but because I have two functions that come together to represent the relation of y squared equals x. Because using mathematics, this says y is equal to plus or minus the square root of x, but my graphing calculator has to do each of them separately. So in the top one, you did y equals square root of x, and in the bottom one, you did y equals the opposite of the square root of x, and that's what produced the relation going sideways. Okay. All right, now, that, when we get into later on, when we get into the college algebra, you'll be glad that at least you heard that. Okay? All right, now, so turn to page 65. All right, now, this should make sense. Is 65, that picture at the top, is it a function?
No.
No, it's not. All right, can it be put in the calculator? Yes, but it has to be put in as two functions connected together. All right. So relation function. All right, now, if you look to page 68, on page 68, there's a whole bunch of squiggly lines, and you're asked, are these functions? Or are they not functions? And therefore, you're looking at whether or not the vertical line test will verify them to be functions, or the vertical line test fails, and they are not functions.
That's not hard.
Not hard. And that's the end of the chapter. All right, so if you'll turn over to page 70.
Oh, no.
All right, 70, there's your chapter review. Now, the R1 says, plot the given equation in the indicated domain. Okay, now, if you wanted to put it in the calculator, in y equals, and see what it looks like, where the domain is all values of x, right, all real numbers, what are you going to have to do to A? You're going to have to get it to algebraically say y equals. So what would you do with A? You would say y equals negative x plus 2. Would you not? You'd subtract an x from both sides, and that's what you put in the y equals. You're going to put negative x plus 2, and it'll show you what the graph looks like. Now, what does the restriction say? It has to be between negative 1 and positive 3. Well, you might be able to read that off the graph, or you could see the values under table to see what the values are. But at least you can see what that graph looks like. Okay? Now, what would happen for B in R1? What happens to B? What are you going to do to be able to get y equals? Yeah, again, subtract the x squared. So now you have negative x squared plus 2, which is a different looking graph. All right, now, the problem with that graph is that it's asking you for only specific points. Okay, now, take your calculator and go second graph, and it brings up a table. So, can you find, what are you going to have to do with your up and down arrows to find what the value of y is when x is negative 2? All right, you're just going to move the graph. So now, could you find the values of y when x is negative 2, negative 1, 0, 1, and 2? All right, because you have just learned to use a tool. Okay? Now, we could have substituted and done it mathematically, done it using arithmetic. But because we're getting smarter in the algebra part, we could actually do that. Now, the problem with C, with C is the one I was telling you about, is that C, when you take the square root of a number, you have plus or minus. When you take the square root of, you have plus or minus. So I want you to put this in your notes. If you have y squared equals x, and then you take the square root of both, you have y equals plus or minus square root of x. And that is because these two negatives, when you square them, will produce a positive. And these two positives, when you multiply them together, will produce a positive. Right? And so when you're going backwards and you take the square root of a square, you have to get a plus or minus over there. And that was the two graphs that we saw in that example. Right? Square root of x is the positive, and then negative or opposite the square root of x, and those two made because the square root graph looks like this. What happens if I flip it? It looks like this, which is a parabola turned and rotated 90 degrees. Right? And so that's how they work. But if you remember, I think, I gave you that list of what those graphs look like. And I told you last week that those were things that 8th graders had to memorize. So that when they got to algebra, they knew that that was a square root function. Because they memorized that as an 8th grader. Right? And they knew that the u was a quadratic function, and that the v was an absolute value function. They learned that in 8th grade, where most of the time today that's not taught, and so you don't have an understanding of what the graph looks like that these things come from. Okay. All right. So, all right. How are we doing? Did we stop?
We ended 10:20.
We ended 20. Praise God. It worked out perfect. Okay, all right, so I'll put this up on the website, on the teacher page, but you're going to be doing 14 to 23, sketching the graph based on what you read. And the things that we did last week, where I gave you a lot of hints to show you how that went, if you actually tried to interpret that, you ought to be able to do 8 of them yourself. Get some of them right. That's this part. All right. There is probably going to be one of those on your chapter test. So it's good to know how to do that. And then the section 2.4 is the one we just got done talking about, where you're looking at whether or not they are their functions and what the graphs look like. And again, you have to sketch the graphs, but use your calculator to see what that graph looks like. And then make sure that you've got it run, and then always take these things and compare your answers with the given answers for this chapter. Make sure that you're thinking along the lines of the dude that does that explains what it's supposed to be look like, the answers look like, so that you are in parallel with him. You're thinking the way he's thinking, because if you are, then when you have the test question, you'll get the test question correctly. All right? Now, and then also, you're going to do R1, R2, and R3. All right? It shouldn't be that long. And that is going to get you ready. And then also notice here that in the published work, that R1C and R1D are backwards. They're reversed. Okay, and so, all right, now let's look at, if you would, really quickly, turn to page 70 in your book. Okay, now, notice that C, the values of C the domain is very large because the values of X go positive and negative in both directions. See that? But look at the values for D. The values of D are only going to be one of two numbers. Right? And so no matter what all these values of X, it's either going to be, it looks like either negative 1 or 2 or something like that. Right? And so the one says X equals 2 and the other says X equals 1. Is that a function? Is D a function? The answer is no, because there's hundreds of values of Y for X equals 1. Right? And there's hundreds of values for Y when X is 2, because they're all stacked on top of each other to make those lines. All right, and I think what they're saying is that the answers in the book, these two numbers were reversed. So C is a function, but D is not. Now, how can you quickly make D into a not a function? This is the trick. Color that circle in. That top circle that's blank, if you colored it in, then you'd have two values of Y for the same X. You see that? So that's what you have to look for whether or not things are functions, is whether or not the ends are open or the ends are closed. Because if they're both closed and they overlap, then you have two X's for the same, or you have two different Y's for the same X. Okay? All right, now we'll finish that, and then we will close up chapter 2 and move to chapter 3 next week. Okay? All right, questions? All right, can you hit that button and turn this off?